Hi viewers, welcome to the second segment of the sixth lecture of online series of lectures on Introduction to Category Theory. So we discussed how we can overlap a product in the last segment. Now we'll discuss finite limits and set. So whenever we have a limit in the context of category theory, we talk about limit of a diagram. Okay? Always remember that. So it's different from the limit notion of calculus. So we have a diagram and we seek the limit of that diagram. Okay? So limit of a diagram will be discussed in fair detail later in this course when we talk about abstract category, okay, in the most general setup. All right. But let me discuss it a little vaguely, what it means by limit of a diagram. A diagram in the abstract setup is a functor. We denote this functor by D from an index category to a given category C. Alright? So we have a given category C and we have some category called the index category. It has to deal with the index family that we have in analysis or in algebra. So it's a generalization of that thing. You can think that way. So we have one category called index category, and we have a given category C, and the diagram is a functor from the index category to the given category. Okay. And one refers to the limit of this diagram functor. One refers to the limit of this diagram functor. Okay. So, a diagram the limit of this diagram functor is a finite one if this index category is finite. Otherwise, the limit is called an infinite limit. So the index category is finite, means it has finitely many objects in the set of objects. Well, in the set of objects, let's call it in the set of objects, and finitely many morphisms in the set of morphisms. Okay. So that was the finite limit of the diagram if the index category is finite. And another thing is that if in fact, the limit of a diagram D, which is nothing but a functor from the index category to the given category C, is a terminal object. I mean that the limit of the diagram D is a terminal object. So it's a terminal object of some category that we call CONE only. So out of this diagram D, diagram functor D, you can construct a category only where there are many objects and these objects are connected by certain morphisms, and the terminal object in that category is precisely the limit of that diagram. Okay? So I told you earlier that I'm doing it a little vaguely because we don't have enough background to do these things very rigorously, but we'll do these things, appropriately later in this course. Okay? So this category has a name. It's called the category of owns to be. The category of owns to be. Right? Okay. So now that we know very vaguely what it means by the limit of a diagram functor, let us introduce, let me give you some examples that you are already familiar with. Examples of finite limits includes examples of finite limits include product, pullback, and equalizer. In the context of the category of set. So in the context of the categories of sets, these are all finite limits. Okay? Product, pullback, and equalizer. When we hold the most general discussion in the setup of abstract category theory, we'll see that these examples of finite limits will appear as special cases of the most general concept of the limit of a diagram functor. Okay, so now let's move to the discussion on coproduct. But in order to do that, we need some background concepts on disjoint union of sets. So let's discuss disjoint union of sets first. Disjoint union of sets. So the disjoint union of a family of sets is a set A which is defined in terms of standard union of these ordered pairs such that X is in AI. So this is the definition of disjoint union of sets. Example. So let us have A0 to be a 3-point set, 3-element set, 5, 6, 7, and A1 be another set whose elements are 5 and 6, so that there is an logical intersection of A0 and A1. We can index the set elements. We can index the set elements above by forming the associated sets So, out of these two sets, we are forming some associated sets of ordered pairs, where A0 star is a sort of renaming the elements of this old set A0 like this: 5, 0, 6, 0, 7, 0. Okay. It's just relabeling the elements of this old set A0. Whereas A1 star reads 5, 1, 6, 1. It's a two-element set. Alright? Alright. So that the disjoint union of these two sets, A0 and A1, is precisely the union of these associated sets. Is the standard union of these associated sets, which is 5, 0, 6, 0, 7, 0, 5, 1, 6, 1. It's a 5-element set, this disjoint union, okay? Okay. So, note that there is a short note here. If we simply denote five, 6, 7 by A, then this joint union of these two same sets is equal to 5, 0, 6, 0, 7, 0, and 5, 1, 6, 1, 7, 1. Meaning that in this disjoint union of the same set A, we have two copies of it, two distinct copies of the same set A. Okay? And this is not the same as A union A, which is just A. Is not the same. Okay? So in general, we have seen that the disjoint union of the two sets A and B is not the same as the standard, the canonical union of the given two sets. Okay? In general, they are not the same. They are only the same when the two given sets are disjoint. Right? They are not the same, but they are isomorphic to each other when the constituent sets are disjoint. So, in other words, let me put it up, highlight it in the remark. The map from the disjoint union of A and B to the union of the canonical union of A and B is not in general bijective, is not in general bijective, so that there is no isomorphism between these two sets. It's not in general bijective. Okay? It is only bijective. It is only bijective when A and B are disjoint. A and B are disjoint. That is, the intersection of A and B is an null set. Okay, good. Now let me define coproduct of two sets. Okay. Coproduct. Let X and Y be sets. The coproduct of X and Y denoted by the disjoint union of these two sets is defined, okay, denoted by this X disjoint Y is defined as the disjoint union of X and Y. Okay, so let me check. I think no, it's going on. Fine. All right. So there are two natural inclusion functions. There are two natural inclusion functions I1 from X to the disjoint union of X and Y, or the coproduct of X and Y, and another is Y to the coproduct of X and Y. Okay, so diagrammatically we write it as these are the two sets that we have in the first place, and these are the two canonical inclusions, and this is the coproduct of these two sets. Okay. So let me give you an example on how to form a coproduct how to form the coproduct of two given sets. For example, A0 is 5, 6, 7, and A1 is 5, 6. Okay? These are two sets. And we have seen that the disjoint union of these two sets is the set of ordered pairs given by 5, 0, 6, 0, 7, 0, 5, 1, and 6, 1, right? So I need to show how these two inclusions look like in this example. The inclusion I1 from A0 to the disjoint union of A0 and A1 is drawn in the following diagram. Okay, where A0 is this three element set 5, 6, 7, and A0 is this 5 element set. A0 disjoint union A1 is the following 5 element set 5, 0, and then 6, 0, 7, 0, 5, 1, and 6, 1. So this is the 5 element set. And the inclusion is pretty simple. 5 goes to 5, 0, 6 goes to 6, 0, and 7 goes to 7, 0. Okay? So this is the inclusion. Similarly, you can construct the second inclusion as well using such diagrams. Okay? So this is an example. Let me give you an example using an O-log now. An example of coproduct using an O-log. Alright? Example using an O-log. So there are two types here for the O-log. One is denoted by X, the other one is denoted by Y. And the label on this type X is as follows: an economy class seat in an airplane. And Y reads a first class seat in an airplane. Okay? And here is the coproduct of these two types, called simply a seat in an airplane. Right? Think about the fact that this is not a set, this is a type. This type is a disjoint union of these two types. You can think of this type as a disjoint union of these two types. If you're comfortable, you can think in terms of sets as well. Okay. So the aspect from X to the coproduct of X and Y, meaning that the inclusion is given by simply ease, and also the other inclusion is also given by the aspect ease. Reading as a first class seat in an airplane is a seat in an airplane, and economy and an economy class seat in an airplane is also a seat in an airplane. So this figure is on coproduct using O-law. Okay. A seat in an airplane is either an economy class seat or a first class seat, and not both. All right. Now we'll explain universal property of coproducts and state a lemma, the first lemma of today's lecture. We'll try to prove it in this segment. Lemma 1. Universal property for coproducts. Let x and y be sets. Okay? For any set A, and functions f from x to A and g from y to A, there exists a unique function. There exists a unique function from the disjoint union of x and y to A, such that the following diagram commutes. Such that the following diagram commutes. Okay, what is that diagram? So this is the disjoint union of these two sets x and y, and we have this inclusion that we already discussed earlier. I1 of x into the disjoint union of x and y, and the inclusion of y into the disjoint union, which we denoted by I2. Okay, and we have this set A and these two functions. One is from x to A and the other one is from y to A. So this is the set A, and there is a function. So for all functions from x to A and for all function g from y to A, there exists a unique function from disjoint union of x and y to A. Okay. We might write this unique function as f of g from disjoint union of x and y to A. Okay? Alright, so this was the statement of the universal property for coproducts. So we'll finish this segment here and we'll carry on with the proof of this universal property of coproducts in the next segment. Thank you very much.